So there are a lot of requirements and there are a lot of rules, and this comes through practice and process, and it'll get easier and easier the more we do it, but it's going to look pretty intimidating here at the beginning. But let's go through the requirements for a covalent compound, a Lewis structure, to be valid. First of all, we have to show all of the valence electrons. For all of the elements, all of the atoms in a compound, we have to show all of their valence electrons. Usually, all of the electrons are paired. More often than not, electrons are going to be in pairs. You will rarely have a single electron. Usually, all atoms need 8 valence electrons. The main exception that we're going to see is hydrogen. Hydrogen only needs 2 valence electrons. Sometimes we can have what are called multiple bonds in order for everything to reach 8. So sometimes you'll have what's called a double bond or a triple bond, where instead of sharing 2 electrons, 2 atoms are going to share 4 or 6 electrons by having multiple bonds. And then finally, each bond always has 2 electrons. So whenever you draw a bond, you're indicating that there are 2 electrons being shared between those 2 atoms. So each bond counts as 2 electrons. Okay, so let's go through the rules. We're going to go through these step by step, and then we're going to apply all of the rules to different examples. The very first thing that you're going to want to do is count all of your valence electrons. So we'll go through, based on the periodic table, how many valence electrons does each atom have, and look at the total. So that's the pooling all of the valence electrons together. The next thing you're going to do is you're going to figure out the central and the terminal atoms. So what's going to be in the middle of your molecule and what's going to be on the outside. So central is going to be in the middle, terminal will be on the outside. Hydrogen atoms are always, always, always terminal. You will never have a hydrogen in the middle of your molecule. Carbon atoms are always your central atoms. In the molecules that we're going to be drawing, your carbon will always be in the center. So carbons are always central. Once you kind of arrange them, then you're going to start drawing your bonds. So you're going to arrange them first, then you'll draw your bonds, you'll draw those connections, and you're going to start with just single bonds. So you'll connect your terminal to your central atoms with single bonds. You'll subtract those single bonds from your total number of valence electrons, and then using your extra valence electrons you have, you'll start completing the octets. You'll start with the outside atoms, and you're going to add electrons until each atom has 8. So once all of your terminal atoms have 8 valence electrons, including the electrons in the bonds, then if you still have extra electrons, you'll go to your central atom and add electrons until your central atom has 8 valence electrons. Now at this point, you might have hit 0. You have no electrons to put in place. All of your terminal atoms have 8 valence electrons. Your central atom has 8 valence electrons. Some of those might be in bonds, but you've reached the end of your electrons. That's fine. If you are out of electrons and your central atom does not have 8 valence electrons, that's when you need to pull in additional bonds. So instead of an outside atom having a pair of electrons, that pair of electrons will become a bond with the central atom. We're going to go through examples that cover every single one of these rules, so we'll look at how they're all applied when we actually draw Lewis structures. Our second example is carbon dioxide, so CO2. Our first step is to figure out how many valence electrons we have. Carbon has 4. Oxygen, we have 2 of them, and each oxygen has 6. So 2 times 6 is 12. Plus 4 gets us 16 total. So we have 16 total electrons that we're working with. So we need to find homes for all 3 of those. Now, our second step is to figure out our central and terminal atoms. We said carbon will usually be our central atom. So we're going to put carbon in the middle. And we're going to put our oxygens on each side. The next thing we're going to do is connect them with 1 bond each. So we have everything connected now just with single bonds. So we started with 16 electrons. We've now used 2 in each bond. So we have 2, 4, which leaves us with 12 left to place. So I'm going to start with my outside. I'm going to put 2, 4, 6. So now I've used 6 electrons, but this oxygen has 8. It has 2 from the bond, 4, 6, 8. Now I'm going to do the same with this oxygen. I have 6 electrons left, so 2, 4, 6, 8 total. I've added 6 more. So I've used all of my electrons. I'm down to 0. My 2 oxygens have 8 valence electrons, but my carbon only has 4. My carbon needs 4 more electrons. So these electrons from this oxygen are going to become a pair. So we're going to have a double bond with our oxygen. So we draw 2 lines. And now we only have 4 pairs. We have 4 electrons just as dots. We took these dots and we made them a bond. So now we have 2 bonds and 2 pairs of electrons. We're going to do the same on this side. So we took this pair of electrons, and instead of it being only on oxygen, we said, let's share it with carbon. So we draw 2 lines to show the 2 bonds, and then we have 2 pairs of electrons on the oxygen. So now our oxygens still have 8, 2, 4, 6, 8, 2, 4, 6, 8. But in this case, so does our carbon. Now our carbon has 2, 4, 6, 8 valence electrons. So we've used all of our electrons, and everybody has 8. Okay, let's look at our last example, H2CO. First thing we're going to do is add up the valence electrons. So we have 2 hydrogens, each with 1, a carbon, which has 4, an oxygen, which has 6, and so we have 12 total valence electrons to work with. So carbon's going to be my central atom, because carbon is usually the central atom. So we'll put carbon in the middle, and we'll put hydrogens and an oxygen around the outside. Okay, so now I've arranged them. I'm going to connect everything with single bonds. And I have a running total of 12. I've used 2, 4, 6, which leaves me with 6 left to place. So I'm going to put them on my terminal atoms. I'm not going to put them on my hydrogens because hydrogen only needs 2. Those are already in the bond, so I'm going to put them on oxygen. Now my oxygen has 2, 4, 6, 8 valence electrons. I've used 6 additional ones, so I'm going to subtract 6 and end up with 0. So all my terminal atoms are good, but my carbon still only has 2, 4, 6 valence electrons. So what am I going to do? I'm going to take this pair of electrons, form another bond between oxygen and carbon. I'm going to form that double bond and have 2 hydrogens still out here. So that would leave oxygen with only 2 lone pairs of electrons. So I've had 12 to work with, 2, 4, 6, 8, 10, 12 total. My hydrogens have the 2 that they're supposed to have. My carbon has the 2, 4, 6, 8 that it needs, and my oxygen has the 2, 4, 6, 8 that it needs, so that everybody has 8 valence electrons. This means that the central atom can expand beyond the octet rule. It can have more than just 8 valence electrons. And we usually see this with elements such as phosphorus, sulfur, and xenon are the most common ones that we see. So phosphorus and sulfur we know are nonmetals. Xenon is a noble gas. This is one of the few exceptions to noble gases don't bond. Xenon will bond every once in a while under very specific sets of conditions. So let's see what this looks like. So if we have PCl5, our phosphorus is going to go in the middle. Let me grab my periodic table. So if we look on our periodic table, we see that phosphorus has 5 valence electrons. I'm going to go ahead and draw those in. 1, 2, 3, 4, 5. But we have 5 chlorines. Now that doesn't make sense. If phosphorus is going to bond to 5 chlorines, that means it's going to have 10 electrons minimum just in those 5 bonds, which tells us that this is going to be an expanded octet. This can happen. If we have a formula for it, we know that this can physically form, at least in our situations, and so we know that this is going to be an expanded octet. So that means each of these electrons, even these guys in the pair, are going to form a bond to a chlorine. So let's draw our chlorines in. And each chlorine has 7 valence electrons. So in this case, in order to form the 5 bonds that are necessary, each of the valence electrons for phosphorus are going to have to bond with the lone electron on chlorine. So there's 1, 2, 3, 4, 5. So it still follows our other rules. We didn't gain or lose any electrons. However, in this situation, instead of having 8 electrons only around the phosphorus, we have 10 because this is an expanded octet. So let's look at SF6. This is going to look very similar. So the fact that we have 6 things bonded to sulfur means that at minimum, we're going to have 12 valence electrons around sulfur. So that tells us that this is going to be an expanded octet, and that's okay. So we're going to put our sulfur in the middle. Sulfur has 6 valence electrons. So that tells us that each of these valence electrons is going to form a bond to a fluorine. So we're not going to have any lone pairs. So even the electrons that are in the pairs are going to form individual bonds to our fluorines. And so we have 6 fluorines. So 1, 2, 3, 4, 5, 6. And each fluorine has 7 valence electrons. And so each of the single electrons on fluorine is going to bond with an electron from sulfur, even the ones in the pairs. So there's 1, 2, 3, 4, 5, 6. So again, we're still following our rule that we didn't gain or lose any electrons. However, sulfur now has 12 electrons around it instead of just its standard 8. So that makes this an expanded octet. And then finally, let's look at XeF4, so xenon and fluorine. So this looks like it might still be okay because it just has 4 things bonded, but xenon's a noble gas. Xenon already has 8 valence electrons. So let's look at what this might look like. So xenon's going to go in the middle, and it's going to have 8 valence electrons. So let's go ahead and draw those in. And then it's going to bond with 4 fluorines. And each fluorine has 7 valence electrons. So each single electron is going to find an electron from xenon. Now, they're all in pairs, so we're going to start by splitting up one pair at a time. So let's split up this bottom pair, and one of those is going to bond with this fluorine, and one is going to bond with this fluorine. And then we can do the same with this top pair. So let's split up that pair, and one electron from that pair will bond with that fluorine, and one will bond with this one. So in this case, they didn't all bond. We have 2, 4, 6, 8 electrons in bonds, and we have 2 lone pairs. So xenon forms an expanded octet, and it can bond with the 4 fluorines. So that's what an expanded octet would look like.